Okay, let's get started. Welcome to Lecture 14 of the Planets. Today, we're going to discuss the planet Earth, its atmosphere, and changes to its atmosphere that are unprecedented. We're going to talk about global climate change, global warming, and the underlying greenhouse effect. Today's lecture is unusual in that the topic itself seems to be politically sensitive. But in my lecture, I'm going to do what a good scientist should do, which is I'm going to present you with facts, with data that have been measured by many scientists, confirmed, incontrovertible, information that you can depend on without any question. And so as I go through today's lecture talking about global warming, you should have a somewhat skeptical voice in the back of your head asking, is this information or is it merely opinion? And I think you'll be able to judge for yourself what it is that you can believe in. And indeed, I'm going to stick to the facts and the data. So let me start by saying that there are two overarching types of information that I'm going to tell you today. The first is that global warming is a measured fact. You will hear people say, well, global warming is just a fiction. It's a fabrication by some political group or other. And I'll show you, I think today that's not true. It's a measured fact. Observable, the warming is in many different ways, many diagnostics of temperature. And secondly, I'm going to talk about constituents in the Earth's atmosphere, most notably carbon dioxide. Carbon dioxide, CO2, can be easily measured, and I'm going to show you measurements of carbon dioxide, measured indeed many different ways, and you'll see the increase in the amount of carbon dioxide in the Earth's atmosphere as an indisputable fact. So keep in mind, as the lecture goes on, what it is that you feel comfortable with and what seems secure in the sense of data, information. Now, the data began back in 1959. A scientist named Charles Keeling decided to measure carbon dioxide in the Earth's atmosphere. He didn't have any reason to think that carbon dioxide was changing in the Earth's atmosphere one way or the other. But he went to a place in the middle of the Pacific Ocean so that the ocean breeze could wash over the island of Maui. And he planted himself near the top of one of the mountains there to measure carbon dioxide. And he, in fact, had to establish some new equipment to measure the carbon dioxide. This wasn't too difficult. Chemists can measure the amount of various types of molecules, and he developed a simple technique for measuring the amount of carbon dioxide in the air. What could be easier? And so he began to do that, and I want to show you now the measurements that he began making back in 1958, 1959. Here you see a graph of the amount of carbon dioxide measured in parts per million. There are so many molecules in the Earth's atmosphere. Per 1 million molecules, how many of them are carbon dioxide? And you see the tick marks, 320 molecules per million, 340 per million, 360 per million. These are units that are less than a part in 1,000, if you think about it, 300-ish per million. And here we have time. He started He started with his very first measurements in 1958. And let me now show you the measurements year after year after year measured from that equipment on top of Mauna Loa. The red line shows the data, the actual data. The black line is just the annual average, the average during a year. People were shocked. How could the Earth's atmosphere be changing so dramatically in the concentration of carbon dioxide on a yearly basis? The Earth has been around for 4.6 billion years. How could the Earth's atmosphere be changing the amount of carbon dioxide from simply year to year? And the increase here from 315 parts per million all the way up now to nearly 400 as of today is obviously an increase of roughly 30% in the amount of carbon dioxide in the Earth's atmosphere. Now, yeah, it's true if you look carefully, you see the red line goes up and down and up and down and up and down, chugga, 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 chugga. Every year the amount of carbon dioxide rises and falls during the seasons. And I think you can imagine why that is. In the summertime, plants are flourishing. Plants, of course, consume carbon dioxide and, by photosynthesis, convert some of it into oxygen. So carbon dioxide is sucked out of the atmosphere during the spring and summer when plants are flourishing in the northern hemisphere. And then in the winter, plants die, they decay, and that carbon dioxide can go back up into the atmosphere as plants decay. Methane, by the way, as well as some other carbon-based molecules. So the up and down is simply seasonal. By the way, you could wonder, well, wait a minute, when it's spring and summer in the northern hemisphere, it's winter, fall and winter in the southern hemisphere. Don't those two balance out? Shouldn't they cancel each other? Well, yeah, they should, except if you look at a globe of the Earth, there's more land mass in the northern hemisphere by chance than there is in the southern hemisphere. North America, Europe, Asia, they're all in the northern hemisphere. And so the plants that are breathing in the carbon dioxide in the spring and summer, they dominate in the northern hemisphere. There's just more land mass and more plants, and hence the annual chugga, chugga, chugga. You can ignore that for the moment and just breathe in that 30% increase in the amount of carbon dioxide in the Earth's atmosphere in just a few decades. Since your parents were born, the Earth's atmosphere has dramatically changed. Well, this is quite remarkable, and it will turn out, as you'll see by the end of the lecture, very important. I can show you some modern data. I think the next slide might have something more up to date. See if I can get there. Maybe I can't get there. There. I pulled this off the web just 10 minutes ago. And the only reason I did is that it goes all the way to 2014.5, i.e. basically today. And you can see the increase in carbon dioxide has continued nonstop, monotonically, all the way through 2014, this year, mid-year, when the last measurements have been recorded. You can bet that next year, when you look at this graph, the carbon dioxide will be even higher. We hit an amazing moment right there, 400 parts per million. And we're going to obviously exceed that in the next winter. So the amount of carbon dioxide is clearly increasing. And the record I just showed you only goes back to 1958, when Charles Keeling started, but we can do better. And you can do better by going to the Arctic and drilling down in the ice that has been piling up by snowing over the centuries and pulling up a cylindrical core of ice, the bottom of which was deposited hundreds of thousands of years ago. And when you drill down in the ice, as was done here at Vostok Station in the Antarctic, you can drill down 3,000 meters, at the bottom of which the snow was deposited there over 400,000 years ago. And of course, trapped in that ice are pockets of air. And those pockets of air tell you how much oxygen, nitrogen, argon, and carbon dioxide there was in the air way back 400,000 years ago. And what you do, of course, is you cut the ice cores, these beautiful cylindrical ice cores, and you measure how much carbon dioxide is trapped in the air in parts per million. And when you do that, you get a record of how much carbon dioxide was in the Earth's atmosphere going back 400,000 years ago. Let me just show you the last 1,000 years. Here you see it. There's the year 1000. You could go back to the birth of Christ if you want to. It doesn't change. And you can see that the amount of carbon dioxide in parts per million was about 280. Through the Middle Ages, the Dark Ages, the Renaissance, here Columbus, and so on. Here's Baroque music, Beethoven. And starting around the mid-1800s, early and mid-1800s, something happened. And of course you know what that is because you've learned about it, the Industrial Revolution. People began building machines that made use of coal. They burned gasoline. There were coal engine trains and locomotion. And that's something that we know happened at that era. But in any case, the amount of carbon dioxide in the Earth's atmosphere has skyrocketed to levels never seen in the last 400,000 years. And in fact, here we are going back to the time of Christ, and you can see carbon dioxide is shown in red, parts per million. There it is, 280, 280. For almost 2,000 years, the Earth's atmosphere was perfectly stable. And indeed, why shouldn't it be? But then around 1830, 1840, the amount of carbon dioxide went literally off the charts. And in fact, nowadays, you see we're at 400 off the chart. And some of the other gases that we'll be discussing today, methane, nitrous oxide, have also risen to levels never seen before. Let me just pause for a moment and remind you that the carbon dioxide data I'm showing you is not at all controversial. Nobody in their right mind would say that these measurements are somehow faked or flawed. They can be made by anybody, and they have been made by many different scientists. This rise in carbon dioxide, either measured by the ice cores or measured by Charles Keeling or anybody else who wants to do it, gets the same answer. The carbon dioxide in the Earth's atmosphere is skyrocketing. It's just a fact. And you might begin asking, what are the consequences of such an unusual, dramatic, unprecedented change? Now, in addition, you can measure the temperature of the Earth's atmosphere by using a thermometer. You can get out your thermometer and measure temperature. Well, that's good, but we've only had excellent thermometers for the last 100 years, and it turns out you can do better than that. And the reason is that if you go back to those ice cores, there are other constituents, notably deuterium, which is hydrogen that has an extra neutron, deuterium, and oxygen that has not just 8 protons and 8 neutrons, but an extra 2 neutrons, making it oxygen 18, an isotope of oxygen. And it's very easy for chemists to measure the amount of deuterium or oxygen trapped in those ice cores. And it turns out when you graph the amount of deuterium or the amount of oxygen as a function of the temperature when the snow fell, the amount of deuterium or the amount of oxygen as a function of temperature, look at the beautiful correlation. When the temperature goes up, the amount of deuterium or the amount of oxygen 18 goes up. What this means is that you can use the amount of trapped deuterium in those ice cores or the amount of trapped oxygen in those ice cores as a thermometer. Measure the amount of deuterium or the amount of oxygen, and then just read off the graph. The amount of deuterium tells you, by reading down here, what the temperature was. For any value of deuterium, you can figure out what the temperature was when that snow fell and got trapped in an ice core. And by doing this, you can therefore read off the temperature of the Earth's atmosphere going back 400,000 years. And let me now show you just the last 130 years. Going back to 1880, this blue line shows you the averages, and you can see the temperature relative to the average, which is placed at 0. The temperature, global surface temperature, was sitting around in here, and then it began rising. It goes up and down, and rising a little more, and rising some more, and in the last 30 years has risen quite a bit. And you can see that by comparing today to the 1800s, we're up about 0.9 degrees Celsius. I guess that's something like 1.7 degrees Fahrenheit. The Earth is warmer now by a degree Celsius than it was. Yeah?
How do you calculate the global temperature for the ice cores of Antarctica?
Well, of course, in this particular case, you're measuring the Earth's atmospheric temperature that determines the amount of each of those isotopes. Let me repeat the question. How do you determine the global temperature based on a local measurement of radioactive, isotopic minerals? And the answer, I will give you a brief answer, but it's a great question, that the amount of deuterium or oxygen 18 that happens to be floating above the Antarctic isn't just a local deuterium, a pocket of deuterium. The Earth's atmosphere has winds. There are global winds. Winds come up from the equator. They blow east to west. So when you measure the air trapped in the ice in Antarctica, you are effectively measuring the air that was swirling around a large fraction, if not indeed the entire globe of the Earth. And you can easily show that. When a volcano goes off in the Philippines, the air in the Antarctic has the soot, the dust from that volcano. In other words, within months, the Earth's atmosphere homogenizes like milk. So this is a pretty good measure of temperature going back 100 years. Here's another view of that same graph going back to 1850. You can see the data points. And, of course, another way to answer your question is that there are other ways to measure temperature. I'm only showing you a couple. You can indeed use thermometers. There were good thermometers in the 1800s, and so there are multiple ways to measure temperature, and they all show an increase in the air and in the ocean. So globally, the Earth has warmed by about 0.9 degrees Celsius, and those thermometers, never mind the ice cores, can be used to show how the temperature rose in different locations. So this is another answer to your question. I'll start this again. This shows over the entire globe of the Earth what the temperature rise or fall was in different regions. White means no temperature change at all. Yellow means an increase in temperature. Blue means it got colder. And if you see over the decades, the Earth, as measured by thermometers by many hundreds of different people all over the planet Earth, the Earth has gotten warmer and warmer. I'll show that again. So starting in the 1880s, there are locations on the Earth where for a few years it gets a little cooler. And there are other locations where it gets warmer. But as the years and the decades go by, on average, the Earth is getting warmer and warmer. Some spots get colder. Look at that. But most of the Earth is warming. That's why people talk about global warming, and other people like to say it's global climate change, because there are locations where it gets cooler because of the flows of the air, dragging air from maybe the Arctic or the Antarctic. But on average, the Earth is getting warmer, and it's gotten warmer in the last century by about 0.9 degrees Celsius. Here's that same graph again, but now from 1960 to 2000. We've had excellent thermometers all over the world in the last 40, 50 years. You can just simply check the temperature measurements made in India, in Moscow, in Sydney, Australia, in Paris, France, in Cape Town, South Africa, and simply determine, did the temperature rise, as shown by yellow or orange, or did it fall, as shown by blue? Yeah, there are some places where the temperature fell here in the Antarctic. There's a spot over there in the Pacific. Something is happening in the flow of water here off of Florida. But for the most part, the temperature has risen a degree in the last century. Now, I've talked about two sets of data, carbon dioxide and temperature. We might ask, are they related? It's a normal thing to ask. So let's compare this increase in temperature with the increase in carbon dioxide, which, as you'll see in a moment, is a so-called greenhouse gas. Here's the graph of temperature versus time that I already showed you. There's the increase over the course of more than a century. And here is a graph, again, that I've already shown you of the increase in the carbon dioxide from ice core drillings going back to 1850. There's the inexorable increase in carbon dioxide. And as I mentioned, some other gases like methane, the nitric oxides. Oh, by the way, here's the CFCs. Remember I mentioned them last time? The chlorofluorocarbons that we humans produce, for sure, rose up out of nowhere, and now we're beginning to curtail our human production of CFCs. Remember the point, as an aside, and be careful, it's the chlorofluorocarbons, the CFCs, that was destroying the ozone that in the stratosphere kept the ultraviolet light from coming to the Earth. That has nothing to do with global warming or global climate change, but just make a mental note. Last time we talked about the CFCs that destroyed the ozone that had been protecting us from ultraviolet, and the ozone had been protecting us, the CFCs destroying it. And so now the countries got together, as I mentioned, and have stopped producing the CFCs. So that's good. Now, going back to this, temperature rose for the last 150 years, and carbon dioxide rose. if you squint, the shapes of those two curves look somewhat similar, and you can now use the ice core drillings going back 400,000 years and graph carbon dioxide concentration over the course of time. It goes down and up and down and up over tens of thousands, 100,000 years, up, down, all the way to the present. That's carbon dioxide. And below, based on the deuterium and the oxygen-18, here's the temperature. It goes down and up and down and up and down and up and down and so on. And it doesn't take a statistician for you to notice that these two graphs seem related to each other. When the carbon dioxide goes down, the temperature goes down. When the carbon dioxide is high, the temperature is high, and so on. They are correlated. There's just no doubt about it. They look a little bit like plate tectonics, how the North and South America snugly fit into Europe and Africa, showing that those two continents were once connected. But here, we're talking about something completely different, carbon dioxide and temperature. The correlation is very clear. And here's another graph, the same data, graphed a different way, carbon dioxide and temperature. It's just data. You can graph carbon dioxide on top of the temperature, both as a function of time, and that's shown here. Carbon dioxide over the course of time since 1880. The carbon dioxide is the red from the ice cores. Here's Charles Keeling's Mauna Loa. There are many other measures. So the CO2 just inexorably goes up. And the temperature, global temperatures, are shown in the blue. Chugga, chugga, chugga. Sometimes high, sometimes low. But they surely track each other. Very much like the previous graph that went back 400,000 years. So the temperature and the carbon dioxide are clearly correlated with each other. When one goes up, the other one goes up. Now, let's summarize all of this because it's just data. You got your carbon dioxide going up inexorably with time. Whenever you breathe in air, you're breathing in 30% more carbon dioxide than your parents did when they were your age. And here is the carbon dioxide going back to the year 1000. And then again, to summarize, there's carbon dioxide and temperature, and you can see the correlation. And then the temperature, of course, itself has been rising. So this is just a summary of data. Anybody can make these measurements. Now, obviously, anybody who's curious would ask, why, oh why, should temperature be correlated with carbon dioxide? One is a measurement of the heat, the motion of the molecules that is temperature, and the other is a molecule, the CO2 itself. Why might they be related? Well, to answer that question, we need to know what determines the temperature of the Earth. And you actually already know the answer to this, but I'll remind you that if you ignore the greenhouse effect for the moment, what determines a planet's temperature, the Earth's or Venus or Mars or Mercury, or for that matter the Moon or an asteroid, is the planet's distance from the Sun and how luminous the Sun is. The Sun is beaming light onto the Earth, which warms up the Earth. The farther the Earth is from the Sun, the less sunlight the Earth would receive. And then, moreover, there's another factor, which is the reflectivity, otherwise known as the albedo, of the planet. So a planet has a certain distance that determines how much of the luminosity from the Sun it gets, but some of that light is reflected away and doesn't heat the Earth or any other planet. It's the light that's not reflected that can heat up the surface of the Earth. Okay, that's fine. High reflectivity means less light absorbed. The planet would be cooler. So the Earth's average temperature can be calculated. And it's easy to do. If you take an introductory astrophysics class, you'll learn how to calculate the temperature of the Earth. And it turns out the temperature of the Earth should be minus 17 degrees Celsius, 17 degrees below freezing on average. Obviously, the Earth is not that cold. Otherwise, we'd all have parkas on in this room, and it would be snowing outside every day. So something else is going on that warms up the Earth above this expected temperature of minus 17. And to sort of illustrate this just a little more quantitatively, let me show a little video. Hey, there's a picture of me. That's pretty exciting. And that's a picture of me in front of a beehive, and the bees are in trouble, but that's another story. I might choose, therefore, to not show this video, but let me just give it one quick shot. If I can get my displays to work, I will do this. But if I can't, I won't. That looks promising. So this shows a graph. Well, it's a cartoon. Sunlight is coming in from the left. And I'm going to put a planet right here, if I can, like so. And my only point for showing this graphic, this cartoon, is to say, here's a little picture from above. There's the sun. There's the planet orbiting the sun at some distance r from the sun. Okay? Sunlight comes in. Much of it hits the planet. Some of it reflects away. You see that as the white arrows. But some of that incoming sunlight heats the planet's surface. That warms up the planet, raises the temperature of the planet's surface, and so it's the distance of the Earth from the sun and the luminosity of the sun that determines what that equilibrium temperature of the sun is. Of what the equilibrium temperature of the Earth is, And I'm going to demonstrate this a little bit better by moving the Earth away from the sun. If I move the Earth away from the sun, these arrows over here got fainter. Let me move the Earth closer to the sun. Notice the solar luminosity gets brighter. Why? Because the Earth got closer to the sun. So the incoming solar radiation depends on how far the Earth is from the sun. And now I want you to notice one other issue, which is cool. And that is, when you move the Earth closer to the sun, not only does the incoming solar radiation, the light from the sun, increase, but in order for the Earth to stay in equilibrium, it has to shed the incoming energy in the form of thermal emission. The Earth's surface gets warm, it emits, guess what? Infrared light, as you all know. So if you watch these red arrows, when I move the Earth away from the sun, the red arrows shrink. When I move the Earth toward the sun, not only does the incoming sunlight increase, but the Earth compensates by cooling itself off, achieving some equilibrium temperature. What equilibrium temperature? Well, that's shown over here on the bottom right. The equilibrium temperature such that the thermal emission from the Earth in infrared light balances the amount of solar light coming in. This explanation, this description I've given you, is something you already know, but I wanted to remind you that the temperature of a planet is something you can calculate. Now, that's all very well if there's no atmosphere at all and no greenhouse effect. So now I'm going to tell you about some physics that's very important and profound. And remember, the Earth ought to be minus 17 degrees Celsius, frigid, were it not for something called the greenhouse effect. I have several slides to describe to you the greenhouse effect, so sit tight, fasten your seatbelt, put your tray table in the upright position. Here's how the greenhouse effect works. Light from the sun comes in. We've already talked about that. What does it do? The Earth's atmosphere is nearly transparent, so the light hits the surface of the Earth, either land or water. That warms up the surface, and by thermal emission, the surface emits infrared light. That infrared light that your own body emits, as well as the dirt outside and the oceans, that thermal infrared light would simply leave the Earth and stream away back out into the universe, like so. Except for the fact that there are molecules in the Earth's atmosphere, notably carbon dioxide and others, that absorb infrared light. And one of those molecules is carbon dioxide. When that carbon dioxide molecule absorbs an infrared photon coming from the warmed up surface of the Earth, that carbon dioxide molecule gets excited, maybe it vibrates, maybe it rotates, I'll talk about that in a minute, and it re-emits light. Having been excited, it re-emits infrared light in some random direction, often back to the surface of the Earth. In other words, the infrared light that would have carried energy away from the Earth got trapped by the CO2 molecule and sent back to the Earth. Very much like a blanket. When you're under the blanket in your bed, the heat from your body can't just leave your bed because it's trapped by the blanket. In this case, the blanket is carbon dioxide, and the heat transfer mechanism would have been infrared light, but it's trapped by the CO2. And here's another graphic showing the same thing. There's the sun, heats up the Earth. Much of the infrared light would be leaving the Earth, having come from the warmed up Earth, but some of that infrared light hits a molecule, gets absorbed, and sent back to the Earth, making the Earth a little bit warmer than it would have been. So here's the greenhouse effect again. Let's see if I can get this to work. This is a graphic showing a planet with first no atmosphere at all. Notice that the planet with no atmosphere is warmed up by its host star, in our case the sun, and the infrared light has no trouble cooling the planet down to colder and colder temperatures. The infrared light is leaking energy back out into the universe. That's fine. But now let's add an atmosphere that has some of these greenhouse gases like carbon dioxide. Every once in a while, an infrared photon that should have left the Earth and cooled it down gets absorbed, re-emitted, and sent back to the surface, keeping the surface warmer than it would have been. Notice this is infrared light coming from the Earth because it's warm. And it's warm because the sun shined visible light on it, as shown above. This is the greenhouse effect. Okay. So, to summarize, let's see if I can summarize. Visible sunlight passes through the Earth's atmosphere. hits the surface, warms up the surface. When the surface is warm, it emits thermal emission, infrared light. That infrared light can be absorbed by molecules and sent back to the Earth, and the result is that the temperature of the Earth is higher than it would have been. We are lucky that the Earth has an atmosphere with some greenhouse gases that perform this greenhouse effect. That has warmed up the Earth above this minus 17 degrees Celsius that would make it frigid. And by the way, when I say frigid, I don't mean it would be uncomfortable. At minus 17 degrees Celsius, if the Earth had no greenhouse effect at all, the oceans would be frozen. The lakes would be frozen. The rivers would be frozen. All the water on the Earth would be absolutely solid ice, and life as we know it would be impossible. So biology on the Earth requires some greenhouse effect to warm us up to the point, 0 degrees Celsius, where some of the water is in liquid form. The greenhouse effect is a good thing. Otherwise, we wouldn't be here talking about it. So let's just spend a moment and try to understand how is it that the molecules absorb infrared light. Well, it's really not that big a deal. I haven't talked about this before. Carbon dioxide molecules have a carbon atom in the center, 2 oxygen atoms on either side. And those carbon dioxide molecules can vibrate. If my head is the carbon atom and my fists are oxygen atoms, I'm a carbon dioxide molecule model. Carbon, oxygen. And the oxygens can vibrate relative to the carbon. So I'm depicting the vibration of a carbon dioxide molecule. This is an energy level. It's a type of energy, vibrational energy, symmetric vibrational energy. And when an infrared photon comes in, it can make the carbon dioxide molecule vibrate, storing that energy in the carbon dioxide molecule. And then when it de-excites back to no vibration at all, the molecule spits out that infrared photon in a random direction. In addition, carbon dioxide molecules can vibrate in other ways. One of them is a bending mode where the carbon atom, my head, and the oxygen atoms, my fists, can move like this. I actually don't know if carbon atoms have eyes that can do that. But if they did, carbon atoms would probably have their eyes open when they come forward. This is another type of vibration. That bending mode allows carbon dioxide molecules to absorb infrared light at different energies, i.e. different wavelengths of infrared light. A diversity of infrared light can be absorbed. And finally, there's yet another mode of vibration for carbon dioxide that's like this. Don't laugh, this is science. So carbon dioxide is quite versatile. It can absorb infrared light coming from the surface of the Earth in a wide variety of ways, and that turns out to be important. These different modes make quite a big difference. By the way, besides carbon dioxide, there are other gases that can also absorb infrared light and therefore serve as a greenhouse blanket, a greenhouse gas. Water vapor, ozone, methane, nitrous oxide, and there are others. Those are the 4 biggies. By the way, the most important, ironically, is water. Water vapor is the most effective greenhouse gas in the Earth's atmosphere. It's not changing with time, however. As a quick aside, this is a complicated graph, but I wanted to share it with you. It shows how transparent the Earth's atmosphere is at different wavelengths. Here's 1 micrometer or 1 micron. The Earth's atmosphere has a certain transparency. At other wavelengths, the Earth's atmosphere is not transparent at all. It's opaque, right in here. 6 micrometers, 7 microns. And it turns out that over here at 14 to 15 microns of wavelength of light, the Earth's atmosphere is highly opaque. Guess why? Carbon dioxide. It's so efficient at absorbing the infrared light coming from the surface of the Earth that it absorbs all of it. And therein lies the greenhouse trapping of heat. It happens by CO2 absorbing the light coming from the surface of the Earth that has these wavelengths. Now, who cares? Well, it turns out, if you remember thermal emission, remember the idea is that something that's warm emits light at all wavelengths, and there's one wavelength at which the emission peaks, a wavelength at which most of the thermal emission comes out. And that turns out to be right here between 14 and 15 microns. In other words, the Earth's temperature is just such that it's emitting most of its thermal emission right where the carbon dioxide bending mode, you remember that one, is very efficient at absorbing that infrared light. We have an extra blanket in the form of carbon dioxide. So you might consider this yet another fact. There's nothing controversial about how carbon dioxide molecules absorb light, and in particular infrared light. And so you can review the facts again, if you wish. Carbon dioxide levels are higher than they were in the past. The temperature has risen almost a degree since 1860. Carbon dioxide correlates with temperature. That's just an observed fact. And now we know one more fact, that carbon dioxide molecules trap infrared light by these vibrational modes. And now you can begin to get an idea of why it might be that temperature might be correlated with carbon dioxide. The carbon dioxide correlates with temperature, that's observed, and the physics of molecules says that the temperature will rise if you put more of this trapping CO2 into the atmosphere. There's really no choice. If you put a blanket over you at night, you will be warmer in your bed. If you put carbon dioxide as a blanket in the Earth's atmosphere, the Earth will be warmer. It just can't be any other way. Very simple facts of physics, you might say. So now we can start putting some of the pieces of the puzzle together, except I want to touch on one issue, and that is, you might wonder whether or not the sun has anything to do with the increase in temperature. Is the sun to blame? Well, the answer in brief is no. It is true that the irradiation, the luminosity of the sun varies over an 11-year sunspot cycle. We'll talk about that next week. Sometimes the sun is a little fainter, sometimes brighter, fainter, brighter. But overall, the brightness, the luminosity of the sun hasn't changed. And so the temperature rise that we've been seeing, the global warming, is not due to our sun. There's another little issue, and that is that some people say, if they don't like global warming for whatever reason, they might say, oh, well, looky here, the global warming stopped from 2000 to 2010. It's kind of flat there. Well, yeah, that's right. And, there are other times when the temperature fell, even quite low, sometimes for, 6-7 years. Sometimes you go for almost 20 years, and the temperature doesn't rise very much. You have to wait 20 or 30 years to see the slow change in the temperature accumulate. It's a little bit like gambling in Las Vegas. You might make bets, and occasionally you win some money, and then occasionally you lose some money, you have to wait for an hour or two at the blackjack table before you've lost all of your money. And so it is with temperature. You have to wait a while to see the accumulation of temperature rise. And this says the same thing, that there are dips and rises and so on. So the temperature rise only shows up in global warming over the course of 1 or 2 decades, not from year to year. So, now we need one more question answered. We've got a lot of pieces of the puzzle. We can understand why it is that temperature rise and carbon dioxide rise might be related, and indeed must be related. The carbon dioxide traps the infrared heat that's coming from the Earth. But where did that rise in carbon dioxide come from? Well, nobody is 100% sure, so what I'm going to tell you now is the first thing I'm going to tell you that has a little bit of doubt to it, but not much. The rise in carbon dioxide over the course of time, you see it here again. I've shown this to you 4 or 5 times. Carbon dioxide rising can be compared to how much carbon dioxide we humans are placing into the Earth's atmosphere. And we do it when we burn oil, when we burn coal, when we burn gasoline, and when we burn natural gas. When you break apart those hydrocarbons, what's spewed out when you burn those fossil fuels is a suite of carbon-based molecules, primarily carbon dioxide. And so you can easily determine how much carbon dioxide we humans are burning, how much fossil fuels we're burning, spewing up carbon dioxide into the Earth's atmosphere. You can estimate it from the amount of coal we're burning, gasoline we're burning in automobiles and aircraft, natural gas we're burning in various ways. And by doing that, you get this graph, and guess what? We are increasing the amount of carbon dioxide we're putting into the Earth's atmosphere. We humans are putting carbon dioxide into the Earth's atmosphere at rates that match well the observed increase in carbon dioxide. Now, this is a fact. We are producing carbon dioxide. This is the amount of carbon dioxide in the Earth's atmosphere. I did not prove mathematically that the carbon dioxide that we humans are putting into the Earth's atmosphere is the actual cause of the carbon dioxide that's rising in the Earth's atmosphere. So I have to stop right here and say, nobody knows for absolute mathematical certainty that the carbon dioxide we're putting into the Earth's atmosphere by our burning fossil fuels is in fact the cause of the rise of the carbon dioxide. But if you've ever heard of the phrase smoking gun, you can draw your own conclusions. And international teams of scientists from all over the world have examined this question, and they've concluded that there's a very high probability that it is indeed the carbon dioxide we put into the Earth's atmosphere that, in fact, is causing the rise in carbon dioxide in the Earth's atmosphere. Yes?
Aren't there different isotopes of carbon that, like, you can tell which ones are natural and which ones are produced, by humans?
Yeah, so the question is, are there isotopes of carbon that allow us to tell which of the molecules that we humans have spewed up into the Earth's atmosphere are the ones that are actually on the rise? And I don't know the exact answer to that question, but I'm pretty sure the answer. There's, for example, carbon-14 in addition to carbon-12. There's carbon-12 is the most popular carbon atom, but there's also carbon-14. And the truth is, when animals die, when dinosaurs die, when plants die and decay and become oil and gas and coal. There's both carbon-12 and carbon-14. Many of you know that carbon-14 is used to radioactively date the fossils, but they're all mixed together. So the poor dinosaur died with both types of carbon, and when we burn that dinosaur in our Buick, both the carbon-12 and the carbon-14 get spewed up into the atmosphere. You can read a lot about this. Some of what's on the web is totally wrong, and you have to be very careful. There are commercial interests in pretending that we humans don't have anything to do at all. But if you look around, and this is a particularly good link, I'll leave this on the PDF so you can see it, where you can see a responsible scientific discussion. Is it possible that humans and our burning of fossil fuels that spews up the CO2 is indeed responsible for the CO2 increase? And as I say, dozens, hundreds of scientists all around the world have studied this, and they've written international reports stating clearly that it is very probable that humans are indeed responsible for the rise in the CO2 in the atmosphere. Now, I want to touch on two last facts. Is it really true that the Earth is warming up? Well, I've shown you two different measurements. Thermometers and the ice core drillings both show the rise in the Earth's temperature. But there's another angle. In addition to verifying that the Earth's temperature is rising, what are the consequences of the Earth's temperature rising? And one of them, of many, is that the glaciers on the planet Earth are melting. Our home planet is suffering from glaciers that are vanishing. And I'll show you a couple. I took a trip to New Zealand specifically to see this beautiful glacier. You can walk on this glacier, you can buy glacier shoes, and I did. You can get these boots and walk on the Franz Josef Glacier. It's on the South Island of New Zealand. You should all go. This is a photograph of that glacier in 1939. You could have gone there with your camera and taken a picture. Here's a picture of the glacier in 1951. Notice the valley. There's the edge of the mountain. There's the edge of the valley. There's the other side. There's the other side. It's the same valley. Notice the edge of the glacier is now here. Before, you couldn't even see it. Here's where the glacier was a decade later, in 1960. There's the canyon walls, and the glacier is going backwards. And now here it is a few years after that, in 1964, Franz Josef Glacier. When I came there, I had to hike for about an hour just to get up to the glacier. There was a point where they said, this is the beginning of the glacier, but there were ferns, plants, so you had to hike to get up to Franz Josef Glacier. It is retreating visibly year after year. And here it is today. Muir Glacier in Alaska, 1941, beautiful river of ice. And here it is in 2004. You see that cliff? That's this cliff. Glacier has gone back a mile. McCarty Glacier in Alaska, 1909. Look at that majestic edge of a glacier. Here it is today. See that peak? That's that peak. See that little mountain? That's that mountain. That one, that one. There's one thing missing, however, from this picture. Columbia Glacier, very famous in Alaska. Beautiful river of ice. There it is. Oops, I passed by it, but you know what I was going to show. below, it was gone. Let's see if I can go back. Oh, there we go. There it is today. Retreated. In just 6 years, glaciers are retreating year by year. Trift Glacier in the Alps. There it was a few decades ago. I think this is 2002, 48, 2002. And there's this beautiful Swiss glacier today. Mount Hood in Oregon. Look at that beautiful volcanic mountain in 1984, August. Here it is today. Easton Glacier. There was the terminus in 1985, and here you see it now, retreating. This is a graph that shows all over the world glaciers and whether they are advancing or retreating. Yellow and red show glaciers that are retreating. Blue shows glaciers that are still advancing and flowing. Yeah, up here in Norway and Sweden, there are a few that are advancing. There's one in Alaska that's advancing. But worldwide, 85 or 90% of the glaciers are retreating. Why might some of them advance? And that is why we call it global climate change. As the Earth warms up, warmer and warmer and warmer, the flows of atmospheric circulation occasionally carry some cool gas, Earth's atmosphere, with some extra water that snows in one place where it didn't used to snow as much. And so a glacier might advance locally, global climate change. But averaged over the Earth, most of the glaciers are vanishing. And I have to tell you, most of you are 18, 19, 20 years old. When you are 40 years old, many of these glaciers will be utterly gone. And when you're a grandparent and you're talking to your grandchildren, you will be telling them about this phenomenon called glaciers that used to exist on the planet Earth. There won't be very many left. Here's yet another graph, retreating glaciers. This is the extent of the glaciers. Each individual graph is a different region of the Earth, a different color: Europe, the Andes, Arctic, Asia. And you can see that worldwide, everywhere, on average, the glaciers are getting shorter. The amount of mass and their length is decreasing. I'll show a little video.
Amid such beauty and so much ice, it is hard to conceive that the Arctic could ever melt. Yet it is. And as the Arctic defrosts, it is having a huge impact on Greenland, which, after Antarctica, contains the world's largest supply of fresh water.
Greenland is actually the biggest island we have on Earth. And the ice thickness in the center is 3,000 meters. That's 1.4, 1.5 miles thick.
The amount of water frozen in Greenland's 1.5 mile thick glaciers is equal to all the water in the Gulf of Mexico. Yet this big ice block is melting, slowly and surely.
The amount that is lost is actually quite large. It accounts to today in the order of 200 cubic kilometers. If you take that volume and put it over the District of Columbia, D.C., it is a water column that is almost 1 mile high.
Is this cause for concern?
It's kind of like a bus parked in San Francisco somewhere starting to roll down a hill. and arguing, is it going 1 mile an hour or 3 miles an hour? The important thing to recognize is the bus is starting to roll down the hill. We know the trajectory, we know the consequences.
The next thing people usually worry about is the Greenland ice sheet. And it's this 2-mile pile of snow, and if that were to melt, it raises global sea level about 23 feet.
Worldwide, hundreds of millions of people near the coasts may be pushed inland, with lowlands like southern Florida threatened with submersion. And major coastal cities, from New York to Shanghai, flooded. And there may be one other negative effect of a Greenland melt. Cold water runoff could divert the warm Gulf Stream from reaching Europe, plunging that continent into a mini ice age.
Some of the reason for the rise in the ocean. Let's see if I can not do this. Boy, that was scary. Some of the reason for the ocean rise is that the glaciers are melting, the ice over Greenland is melting and filling up the ocean, the ice and snow in the Antarctic on that continent is melting and flowing into the oceans, raising the sea level inch by inch over the decades. There's a second reason that the sea level is rising, and that is that as the Earth warms up, the water in the oceans expands. When things heat up, they expand. So believe it or not, and you have to think a little bit, the ocean with its depth of, say, a mile deep typically, if it expands even 1%, that makes the sea level higher than it would have been simply because the water is warmer and expanded. For both reasons, extra melt from the Arctic, from Greenland, from the glaciers, adding to the water, and the expansion thermally of the water is making the sea levels rise. How much? When you're a senior citizen, when you're 50, 60, 70 years old, how much will the oceans have risen? Well, there are various estimates, and this, of course, can't be a fact because it's a prediction. And predictions are based on models and theories and calculations. But most of the predictions suggest that the sea level will rise by something like about 0.5 meter to 1 meter. In other words, sort of the height of this podium. In other words, sort of chest high. All the oceans will be risen by a few feet. Maybe the scientists are wrong and the oceans will rise less. But maybe the scientists are wrong and the oceans will rise even more. And there are reasons to think that there's a possibility of both. I'll finish with one last important thing. I'm not sure if I can get to it. Let's see if I can. Yeah, I might not be able to. Let's see. Hang on. Oops. Well, I lost my video, but it's not important. The last thing I want to say is that the United Nations has gathered together a so-called intergovernmental panel on climate change, global warming. They've met every year for many years. They have committees. They're studying global warming, and they have issued a report as of a few months ago stating that global warming, global climate change is definitely happening. The carbon dioxide levels are definitely rising, and that there's a very high probability that it's the human burning of fossil fuels that is increasing the amount of carbon dioxide, which in turn is serving as a blanket, warming up the Earth. And so one of the issues that you will be hearing about for the rest of your lives is the improved measurements of global warming, but more importantly, efforts being made to stop global warming, or at least slow down the global climate change. How can that happen? By alternative forms of energy instead of just burning fossil fuels, using other sources of energy like solar or wind power, or maybe even nuclear energy, ways that you can acquire energy for your uses but not spew up carbon dioxide into the Earth's atmosphere. So one of the issues that you'll be faced with in your generation is finding economically sound, economically viable ways to motivate other energy sources besides just burning oil, gas, and natural gas and coal. So I'll stop there.